Welcome to Next Gen Manufacturing, the show where we pull back the curtain on how we build the world of tomorrow. Today we're diving into a material that is quite literally the hidden backbone of high-performance manufacturing. You'll find it in everything from wind turbines to spaceships, but you almost never actually see it. So let's get into it.
You know, this is the million-dollar question in modern engineering, isn't it? Whether you're designing a fighter jet or a brand new electric car, you're always fighting this battle between strength and weight. You can't just keep adding more steel or aluminum. So what's the answer? How do you get stronger without getting heavier?
And yeah, I know what you're probably thinking. Sand? Like beach sand? That's exactly right. Sand is the main ingredient for glass. But here's the thing. When you apply some truly incredible manufacturing science, you can transform that everyday glass into a very, very specific form, and it becomes one of the most powerful and versatile materials we have.
So, here's how we're going to break it all down. First, we'll get into its shocking strength. Then, we'll decode the different types, the glass fiber alphabet, if you will. We'll see how it's actually made, explore its different industrial forms, and finally, we'll look at how this stuff is quite literally building our future.
Okay, first things first. We need to do a complete reset on what we think about glass. The pane of glass in your window? Sure, that's brittle. But that's what we call bulk glass. When you pull that same glass into incredibly thin filaments, its properties change. They change dramatically.
Just let that sink in for a second. Stronger than steel. This one single fact is why glass fiber is such a game changer. See, by drawing glass into threads that are just a few microns thick, you basically eliminate the microscopic surface flaws that make a big sheet of glass so weak. You're unlocking its immense raw molecular strength. It's just incredible. But of course, in next-gen manufacturing, one size never fits all. It just doesn't work that way. So by tweaking the chemical recipe of the glass itself, engineers have created this whole family of fibers. Each one is optimized for a very specific job, and they're all identified by a single letter.
Think of it like a manufacturing alphabet where every letter represents a superpower. So E-glass, which stands for electrical, is the workhorse. It makes up more than 95% of the entire market. But then you have the specialists. S for superior strength, AR for alkali resistance, which is great for cement, C for dealing with chemical corrosion, and D for its unique dielectric properties, which actually makes it transparent to radar. So let's compare the two big ones for structural stuff. You've got E-glass, the undisputed king of the market. It gives you fantastic performance for a pretty moderate cost, and that's why it's in everything from boats to circuit boards. Then you have S-glass. Think of S-glass as the elite special forces. It costs more for sure, but for something like a helicopter blade where failure is absolutely not an option, that extra 20% in strength is everything.
And this chart really shows you the trade-offs that are at the heart of all manufacturing. You can't have it all, right? S-glass is the clear winner for mechanical performance. That's your aerospace stuff. But look at AR glass. It totally dominates in chemical resistance, perfect for construction. And what about E-glass, the market leader? Well, its secret weapon is something called fibrability, which is just a fancy word for how easy it is to manufacture. That ease of production is exactly why it's the most common type out there.
Okay, so how do we actually get from a pile of sand and other minerals to these amazing high-tech fibers? Well, the process is a total marvel of precision engineering. It combines blindingly hot temperatures with unbelievable speed. Today, the standard is something called the direct melt process. It all starts with a super precise recipe of raw materials. They're all mixed and then melted down into this perfectly liquid glass. That molten glass then flows into what's called a bushing. It's this precious metal plate with literally thousands of tiny nozzles, and that's where the magic happens. The glass streams out, and it gets pulled into these ultra-thin filaments.
And when I say pulled, I mean pulled. This is happening fast, incredibly fast. We're talking speeds of over 20 meters per second. That's almost 50 miles an hour. This rapid-fire drawing is what stretches the glass and aligns its molecules, giving it that final super strong form.
But right as the fibers are being drawn, one last absolutely critical step happens. They get sprayed with a chemical mixture called sizing. Now this coating does three vital things. First, it protects the brand new filaments from rubbing against each other and breaking. Second, it helps them bundle together into a nice, neat strand. And most importantly, it acts as a chemical handshake, the perfect bond between the glass fiber and whatever plastic resin it's going to reinforce. Without sizing, your composite would just be weak plastic with some loose glass in it.
So, we have our super strong threads. Now what? You can't just hand a factory a single microscopic filament and say, go build something. The next step in this whole manufacturing chain is to bundle these fibers into forms that are actually usable for industry.
The most basic form is what we call a roving. Just imagine a giant spool of thread, but instead of cotton, it's made of thousands of these continuous glass filaments. This format is absolutely perfect for automated machines that can just continuously pull the fiber to, say, wind a high-pressure pipe or pull a super strong structural beam.
Next up, you can take those rovings and you can weave them, just like you would cotton or wool. You can create a high-tech canvas. The huge benefit here is that you get predictable, uniform strength in specific directions, right along the lines of the weave. This is the foundation for things like printed circuit boards and the super strong hulls of high-performance boats.
And finally, for parts that have really complex curves and shapes, there's chopped strand mat. For this, they take the rovings, chop them up into short little pieces, and then spread them out randomly to form a sheet. This gives the material equal strength in every single direction, and it's fantastic for laying into a complicated mold.
So we have the specialized fibers, we have the industrial forms like rovings and woven mats. Okay, this is where it all comes together. Let's look at how these humble components really power the world of next-gen manufacturing.
And the impact is it's everywhere. Remember that high-performance S-glass we talked about? That's what's in helicopter blades. Our glass, which is a close cousin, is what makes those gigantic, massive wind turbine blades possible. That woven E-glass fabric, that's the very foundation of the circuit board inside the phone you're probably holding. And AR glass is letting architects design concrete structures that would have been completely impossible just a few decades ago.
So, when you step back and you really look at the landscape of modern technology, you start to see these invisible threads of glass fiber running through almost everything that's built for serious high performance.
It really all boils down to this. Manufacturers have managed to create a material that combines the best properties of everything else into one amazing package. You get the strength of metal, but without all the weight. And when you combine it with plastic, you get this incredible moldability and versatility. It's a true force multiplier for engineers.
Which, leaves us with a really fascinating question. We've seen how this material, which starts as humble sand, has become a genuine superpower in manufacturing. As we keep developing new glass chemistries and inventing new ways to weave and combine these fibers, well, the possibilities are pretty much limitless. The next revolution in manufacturing might just be waiting to be woven from glass.